All right. Good evening, everyone. So let's see. We have 11 people in here already. So I think it's been already a couple of minutes, so we can go ahead and start. Um, so first thing first, I'm gonna ask you guys to confirm if you can hear me okay and see my screen. If you can confirm, then I'm gonna go ahead and start. All right. So in the chat box, I have it. Affirmative answer. All right. Thank you. Thanks, Luke. All right. So let me know if there's any problem in the meantime. So, or if you have any questions, you can stop me. I'm okay with that. My name is Dr. Ibrahim Al-Bayrak. So I'm gonna be the physics instructor in this semester for Physics 1 course. Um, so I'm excited to have you guys in my class and to learn physics. So a little bit about me. So I'm an experimental nuclear physicist. I'm working at Thomas Jefferson National Accelerator Facility in Newport News, Virginia. It's one of the Department of Energy national labs. Uh, it's um, it's a nuclear research facility. So we're doing nuclear physics here. I have a lot of teaching experience in addition to my research. I taught a lot. I taught at various institutions, like from high school level to graduate level university, and I also taught various topics in physics, like introductory physics courses, like Physics 1 and Physics 2, and also graduate level physics courses like nuclear physics, quantum physics, general relativity, etc. Um, so I think that's pretty much who I am. So since I believe from my previous experience, some of you guys, maybe all of you guys, this is going to be the first exposure to physics. So I just want to talk a little bit about physics before I introduce the class content. Because again, so I believe for some of you guys, this is going to be the first time you're seeing physics. And for some other, especially for those who had not so nice physics introduction, because some physics teachers makes it not very pleasant. Some students don't like physics because of the way it's introduced to them. So I'm just going to give a little motivation, a couple of minutes, and then I'm going to talk about specifically what we're going to be learning this semester. So physics, in my opinion, is not just like formulas and solving problems, complicated problems. Physics is all about understanding nature, understanding the world around us. That's what physics is. But sometimes, yes, it requires solving problems, learning some mathematics. Yes, that it's required. It requires sometimes that, but it's not just mathematical formula. It's just understanding the nature around us. That's what physics is. I So for this, we want to understand. I mean, physics is a very broad range of science. It's not just something simple. It's very broad range of physics, and no physicist is expert in all the areas of physics. Everybody is have expertise in some certain areas because, again, it's a very broad range of scientific um, uh, discipline. Physics is all about understanding nature from the smaller scales, like from quarks and gluons inside the nucleus to the larger scales, to the whole universe, right? So that's what physics is, and that's what physicists do. Right? So we want to understand essential building blocks of the universe, like matter, light. So what makes this universe, right? That's what we want to understand. This is one of the things physicists are interested. And then we want to understand how these things interact with each other, right? Because there's constant interaction with the objects in nature, right? It's not just understanding protons, neutrons, electrons, or billiard balls, right? Not understanding cars because these are also interacting with each other, right? So another part is understanding the interactions between objects, basically understanding the fundamental principles that govern the universe, right? So all of these things. And then finally, we want to understand the structure of space and time. So in addition to the things that makes up universe, we also want to understand the arena behind the scenes, the space-time itself, right, and the evolution of the universe. So all of these things are the physics. Physics is all about. So okay, so physics is all about understanding the nature, universe, the world around us, and then if you guys are following, or probably everybody is hearing, right, from social media, from television, or science channels, etc. So you're gonna hear a lot of like scientific information, knowledge. So you're gonna get an impression that we know a lot about nature. We know a lot about physics of the universe, right? So that you're gonna get that impression. We know a lot of things. That's partially true, but that's partially not true too. So I'm gonna give that impression. I'm gonna try to give that also to you. So how much do we know about the universe, right? Physics is all about universe, but how much do we know about universe? So from the beginning, I can tell you that according to current physics, 95% of the observable universe is unknown to us. So we actually don't know everything, right? So you're gonna get impression that physicists know almost everything. We solved all the problems, but well, that's a kind of small lie, right? So we don't know everything about universe. So actually, there are more things that we don't know than the things we know. So if you compare, if you judge it by the questions we have about the universe, actually we know less compared to 100 years ago, right? Because 100 years ago, people had less questions to answer. But today we have more questions to answer. Although we have more knowledge, but we also have more questions. So in that sense, we still have a lot of things to discover physically, right? So 95% of the universe is unknown to us. So what is this 95%, right? And I also say observable universe. So that means there is also a part of the universe that is unobservable, that we cannot know. So the total size of the universe or total extent of the universe, we still don't know. So everything we talk about physics, we are talking about the observable universe. We are talking about the universe, the part of the universe that we can observe with telescopes. The rest, we can never know, right? Because our telescopes don't reach that part of the universe, so we can never know about that part of the universe. So physics also is all about the observable universe, and of the observable universe, we know 95% of it. So what is the rest of it? So again, 5% of the universe is the universe, part of the universe we know all about. We have physics theories on them. So it's just planets, stars, galaxies, atoms, molecules. This is just the 5% of the universe. So what is the rest? Well, according to current understanding, about 27% of the universe is called dark matter, right? So this 5%, 27% or 95%, this is the energy content of the universe. So this is not just the knowledge, it's just I'm talking in terms of the energy content of the universe. So known ordinary matter that makes galaxies and stars and us and everything else we can see, it's just the 5% of the universe. So the rest, there's another type of energy and also matter that contributes to gravity, but we can't know, we don't know, right? But we know that there must be something out there. So almost 27%, the big portion of the universe, right, is called dark matter, right? So we don't know what that is because that's why we call it dark matter, right? So how do we know that there's such thing called dark matter? So Newtonian gravity, right? So if objects have mass, right? Let's say you have a massive object, and then there is a gravitational attraction between massive objects, right? So if there is no gravitational attraction, and in large scales, that's the only force, that's the only dominating force we have. So we don't have electromagnetic forces, we don't have anything else at large scales. So it's the only type of force that dominates at large scales. So normally, if you don't let's imagine this star, for example. So if there's no force around it, if there's no matter around it, right? So when you watch the star with your telescopes, you're gonna see that star is going straight, right? I'm roughly trying to give you an idea, right? So it's gonna go straight. But when you watch some of the stars and galaxies, you're gonna see that they're not going straight. Rather than going straight, they are following a weird path, a curved path. Let's say something like this, right? But wait a minute, there you don't see anything else around this star. So why would it move like this, right? Why would it move like this? Because you don't see anything around it. So what you say is, well, the only dominant force at large scales is the gravity. So there must be some gravity that pulls this star and changes its course, right? Changes its trajectory. So that means there must be something here, right? We can't see, but it must be there because it's causing some gravitational force, gravitational pull, and it changes the trajectory of the star or galaxies or whatever. So this is what happens when you watch some objects at large scales. So you cannot explain this motion with the existing observable matter, with like regular stars, galaxies. So there's some unobservable things there that also apparently applies gravity. So this is what we call dark matter. All right. So we call it dark because we don't know what it is, because it's not composed of atoms and molecules. It's something else. We call it matter because it has gravity, right? It has gravity. So we call it matter. And we call it dark because we don't know what type of matter it is. It's not the ordinary matter. It's not the ordinary matter that is composed of atoms and molecules. It's a different type of matter. So this is the 27%. So we see this everywhere in the universe. So big portion of the universe we believe that is composed of this whatever dark matter is, right? So because otherwise we cannot explain the motion of objects in space. And then the biggest portion of the universe is called dark energy, almost 67%. Okay, so and then what is dark energy? If you ask that question, dark energy and dark matter are different things. So I explained what dark matter is. Dark energy, so we call it dark again because we don't know what that energy is. But it's not matter because, right, matter has gravity. So dark energy does not have gravity. Actually, it has anti-gravity. So dark energy is the thing that makes universe expand, right? That makes universe expand. So today, probably everybody knows that our universe is expanding. But if I don't know if any of you guys have asked the question, why is it expanding, right? Why would it expand? Because everything in the universe, as far as we can see, has gravity, right? Like stars, galaxies, clusters of galaxies, everything. Everything has mass, and massive objects has gravity. Gravity means, right, attractive force. So everything is actually pulling each other. So universe shouldn't be expanding. Universe should be collapsing. There is gravity in everything, right? And gravity is an attractive force. So what's going on? Why would the universe expand although gravity is pulling everything inwards, right? But when we look out using our telescopes, we see that universe is expanding. So what's going on here? So this is also one phenomena we cannot explain. We don't know, right? We don't know why universe is expanding. So we are assuming that there must be a type of energy, that type of energy that cause anti-gravity, right? And then we call it dark because we don't know what that is, because we cannot explain this behavior. Otherwise, everything should be collapsing, but the universe is expanding, not collapsing. So there must be another type of force. There must be another type of effect that pushes everything apart. So that's what dark energy is. And if you compare the amount of this energy to the ordinary matter, then it's almost 68% of the energy content of the universe. It's more than the ordinary matter in the universe, right? So this two parts of the universe we still don't know, and then there's active research going on either dark matter and dark energy to understand this phenomenon at large scales. And in smaller scales, the situation is not clear, right? So I'm a nuclear physicist. We're trying to understand the structure of atomic nucleus, and it's very complicated. We're still not there that we can say, okay, we understand everything in the nucleus. We don't. It's also very complicated. There's still active research going on in the smaller scales too. So at larger scales and smaller scales, we have a lot of questions unanswered. So that's the humble view of physics I just wanted to give you. All right. So this is what physics is, and this is how much we know about the universe. All right. So let's talk about the physics we know today, right? So that was the part of the universe that we don't know. That's the questions in general, right? We couldn't answer. So what do we know about the universe? So let's go there, and then I'm gonna go from here to the physics class we're gonna be learning this semester. So at larger scales, I'm not gonna go to the whole universe, of course, but at larger scales, let's say we have galaxies, right? So I mean, the objects at large scale. So also, although we have clusters of galaxies or even larger type of objects, but I'm not going to go that far. So let's say we start with galaxies, right? So let's say galaxies are the largest objects we observe and try to understand. And then in smaller scales, we have, let's say, systems, right? Solar system like our planet system. And then even in smaller scales, let's call it human scale, right? Our scale, the world around us, around human being. And the size of these things, so the size of the whole universe is, right? So I'm going to come to that in a minute. The size of the galaxies, like the average galaxy is 30,000 light years. And then our solar system is 8 light hours. So it's not even light years. Compared to galaxy, it's very small. And then human scale physics, so it's even smaller. So we're talking about meters now, not light. We're not measuring distances by light anymore, right? That's human scale physics. So human scale physics, we call it classical physics because that's the physics we started developing in 1900s, right? And then if you go even smaller, then you come into the world of molecules and then atoms. So it's even like smaller scales, 10 to negative 10 meters. It's also called angstrom because meter is not a good unit in this scale. So we use different units like angstrom, like Fermi, femtometer, nanometer, picometer. These kind of units we use to describe distances, right, in atomic scale. But it doesn't end there. So this is atom. Atom means we have a nucleus and then we have electrons around the nucleus. So, and then we also are interested in understanding the nucleus itself, right? So what is it composed of? There are the protons and neutrons inside the nucleus. But inside proton and neutrons, there are also other stuff, right? So this is what nuclear physics is all about, right? So understanding the structure of nucleus, understanding the structure of proton and neutron. So this is my research area. So, and then inside proton and neutrons, today we believe that there are quarks and gluons, right? Quarks are the particles, gluons are the particles, you can call it again, so that carries the force between these quarks, right? So, and then that's the smallest scale we know. So we don't know how big these guys are. So if you ask me to tell you how large these quarks and gluons, I'm just gonna tell you it's their size is 0, right? Because that's, as far as we know, they're point particles. We don't know their sizes. They're so small, right? So we don't know anything smaller than these. That's the smallest scale. So this is the physics today we know from largest to the smallest scales. So what kind of physics we apply to understand? So that's also the humble view I just want to give you, all right? So physics is not a single theory. So we have a physics theory that we use to explain larger scales. The most modern theory we use is general relativity, right? You heard of it, I guess. So it's Einstein's general theory of relativity. So that's the theory we use to explain the physics at large scales. But unfortunately, this theory does not work at small scales. it's not even it's just not work. It's even contradictory, right? So it doesn't work at small scale. So general relativity works in only in like large scale phenomena. When you try to apply it to atoms, it crashes. It doesn't work, right? So at smaller scales, we have quantum physics. Quantum physics explains the physical phenomena for atoms. It's the physics of atoms and molecules, right? How electrons are distributed in atoms, etc. But quantum physics, even if it's for atoms, it doesn't work in nucleus. So for nucleus, we have a different type of physics. It's a nuclear physics. Actually, nuclear physics is not a physics theory. So at smaller scales, we use quantum electrodynamics and quantum chromodynamics. So quantum chromodynamics is basically the physics of these quarks and gluons. That's what quantum chromodynamics is. And then quantum electrodynamics is the physics of electrons and light, right, in smaller scales. So these are the physics theories we use. And again, so none of these theories are compatible with each other. So we don't have a physics theory that works everywhere, right? So we have, it's like patching or fixing a fabric that is torn at several places. So you're just applying patches to cover those torn places. But we don't have a perfectly working theory that explains everything, right? So these theories we use, this is today's physics. And then again, sometimes these theories are even contradictory each other, like general relativity rules doesn't work in smaller scales. So that means quantum chromodynamics and general relativity, these have contradicting ideas between each other. So you cannot apply quantum to galaxies and you cannot apply relativity to atoms. They work in their application of domain, all right? So this is the physics knowledge we have about the observable universe. And again, in the previous slides, I already told you about the universe that we already don't know, right? So this is just 5% of the universe. This whole physics we know all about. The physicists you see in social media or science channels, they are just studying one of these things. It's just 5% of the universe, right? So in this course, we are going to study one part of the classical physics, right? So classical physics or human scale physics, it's mostly classical mechanics, right? And then electrodynamics. Electrodynamics. So classical mechanics in introductory physics. So we most of them call it physics 1. And then this is taught in physics 2, right? If you want to learn like in more details, this is classical mechanics. I mean, it's a separate course at university level. It's classical mechanics. And then if you want to learn in more detail electrodynamics, it's called electrodynamics course. Right? So this is the part we are going to be learning here, physics 1. So classical mechanics. So motion of objects and stuff. So I'm just going to now go ahead and introduce the stuff we are going to be doing this semester. So this is AP Physics 1 course. In this course, we're going to focus more on concepts like mechanics, motion, and stuff. I'm going to go into that in a minute. The pace is going to be slower because I believe, again, as I told you, this is going to be the first exposure for some of you guys. So I'm going to try to be a little more careful there. So I'm not going to try to be like very detailed or I'm not going to expect to memorize a lot of formulas. So I believe some of you guys are going to be taking the first time physics, although this is AP Physics. So AP Physics means college level physics, right? So you're taking college level physics here. But again, I believe some of you guys are taking first time physics. So I'm going to be observant of that. And then this course will also prepare students for the F equals MA test or competition, whatever it is. So it's going to help with that too. There's gonna be homework. So this is the schedule we have. Let's not go to homeworks. So our classes are gonna be on Sunday between 6 and 8 Central Time. So I'm in Eastern Time. So in my time, I think it's gonna be 7 to 9, and then 6 to 8 Central Time. This is the class time. So I'm gonna be delivering the lectures here and solving some problems. And then Thursdays, just 1 hour between 7 and 8, we're going to be doing homework problem solving, right? So you're going to be doing your homeworks, and then we're going to be solving those homework problems together separately on Thursdays. Class starts January 26th, I believe. So it's going to be 16 weeks, right? So and there's gonna be some holidays and stuff, so there's not gonna be class in those dates. And then if something emergency or urgent happens on my side, I'm gonna let you guys know that we're gonna be postponing the class on that day or not. So you're gonna be notified. So Sunday lecture, Thursday homework sessions, and then you're gonna be getting 5% discount if you sign up today or tomorrow. That's from Momentum Learning. And then I have a question in the chat box. It says, how much does the class cost? Okay, that's a good question. Uh, I don't know. So I don't know the cost of the class, isn't it here? So I think you better ask Momentum Learning that question because yes, I'm just a teacher. So uh, the actual cost. I mean, I think it's written in the website. I saw it sometime, but I don't want to quote a number because it might belong to previous classes. So I don't want to say anything right now. But I believe if you go to our website, the Momentum Learning, it should be there, right? The cost of the course. So I'm sorry about that, but I believe that information is on the website. Yeah. Yeah, so there's gonna be weekly homeworks. It shouldn't take more than 2 hours. So you're gonna be working on it, and then we're gonna solve those problems on Thursdays. Okay. Intro to physics, prerequisite 8th to 10th graders who have completed geometry. Yeah, so you're gonna need to have some geometry information. I'm not requiring or expecting any physics background before. So I'm aware that some of you guys are going to be taking physics for the first time, so that's okay. And I hope we can handle it together. Okay. So since you're going to be taking this first time, maybe I should say that too. So please be active in the classes. So I'm not expecting any students to know anything. Right? So it's okay to ask a lot of questions, and please ask questions because I mean, this is an extra course. You're taking it. Your parents are paying for this. So please make sure you understand everything. You get the maximum what you want to get from the course. Okay. Don't be silent because I mean, that's my experience. This is an online course. It's not like a one-to-one. So my I mean, I'm limited here, right? So I'm just on the camera. So please, so I'm gonna try to be very responsive. But again, so if there is anything you don't understand, unclear, just ask questions. That's why I'm here, right? That's what teachers for, right? So you should ask questions, please. And again, I'm not expecting you guys to have any previous physics knowledge, so it's okay, even if you don't know anything. Right? So this is gonna be the first time. It's okay. Please ask questions, stop me, make sure you understand, right? So these are the topics we're gonna learn. Did I forget anything here? I don't think, okay, I think I went over everything. So these are the topics we're gonna go through. So kinematics, just one-dimensional motion. Actually, let me go ahead and then show because I have some slides. So these are um, the topics we're going to learn every week. I don't want to go over all these things. So like we have 16 weeks. The important thing here is we are going to have a midterm exam, and then we're going to have a final exam. So midterm exam is going to be week 7, and final exam is going to be the final week. So, and other than that, so these are the topics. So they're distributed in 16 weeks. The week 15, I'm gonna do a review. So I'm gonna end with rotational dynamics, and then that's it. So I don't want to go over all these things week by week. All right. So again, the important things we're gonna have a midterm and then a final exam. Of course, you're gonna have every week homeworks too. All right. Okay. So first week, we are going to start reviewing some useful concepts in physics. So this is not physics, but useful concept in physics, the things that we're going to use to understand physics, right? Such as measurements, coordinate systems, right? Because we're going to be for example, studying an object, motion of an object, right? So we are throwing an object and then we're studying its motion. So to define the motion, we need a space, right? So to have space, we need a coordinate system because we want to know the position of an object every second, right? So for that, we need a coordinate system. So we're going to study coordinate systems. We're going to study measurements because when we want to know the position of an object, for example, we want to know how to define distances, how to define time, right? So we're going to say at 1 second, this object is going to be at 1 meter. At 2 seconds, the object is going to be at 2 meters, etc. So we want to review the basic concepts such as length measurements, time measurements, and mass measurements, these kind of concepts, because we understand universe, right? As I said earlier, physics is all about understanding universe. And we understand universe by doing measurements, right? So that's how we interact with the universe. We perform measurements and then we measure the universe. We try to understand universe through our measurements. So that's the first thing. And then after that, we start physics. So the first thing we're going to do is we are going to study motion of an object. It's called kinematics, just motion of an object, how objects move in one-dimensional space, right? So in here at the beginning, we're not going to consider two-dimensional or three-dimensional motion. It's just one-dimensional motion. So objects that goes straight in a line, right? So we're going to study that motion. We're going to learn how to get the position of an object, how to find the velocity of an object, how to find the position of object from velocity and acceleration of the object, etc. So we're going to derive those kind of equations that gives us the position, velocity, acceleration of an object related to its motion throughout its life. And then we're going to add one more thing into this motion. So we're going to study motion in 2 dimensions. So, and it's everything in this part of the course is, there's nothing new. It's just analogous to the one-dimensional motion. So 2-dimensional motion, we're not going to derive anything new, right? All the equations and everything is same. It's just 2-dimensional motion. So we are going to do the analysis, the motion analysis in 2 dimensions separately, in X direction and in Y direction. That's it. It's very simple. So as long as you learn one-dimensional motion, the rest should be very straightforward because 2-dimensional motion is just two one-dimensional motion. So one-dimensional motion is the most important part of it, and it's easy. And then 2-dimensional motion is just two one-dimensional motion. So it's nothing different. And then, so that was kinematics, just the motion of objects. But we up to this point, we don't ask questions, what makes object move? Right? Objects move. But what makes object move? We don't ask that question up to this point. And then after that, after learning kinematics, we're going to ask that question, what makes objects move? That's the force, right? Forces make objects move. And then, so that's called dynamics now. So we learn kinematics first, and then we introduce dynamics, which means we introduce the concept of force. Okay. And then I have another question in the chat box. If acceleration is changing at every unit of time, how can we tell the exact velocity of object at any point in time? Well, that's a perfect, good, excellent question, but that's the question we're going to try to answer in this course, right? Not here, but so please record this question and ask me that when it comes to that point, okay? That's a good question. And the relationship between acceleration, position, and force, etc. All right. So we introduced the concept of force that makes objects move, etc. And then after the concept of force or dynamics, we are going to study another very important topic in physics. It's work and kinetic energy. So, or energy in general, energy or power, concepts of energy, power, etc. So these are very important in physics. So we're going to introduce these concepts: energy, work, power, kinetic energy, potential energy, etc. These kind of things we're going to learn and study. And then after that, another important concept, momentum in physics. So these are very useful concepts. So a concept of energy is very useful to solve some very complicated problems. So a concept of energy makes our lives a lot easier. Just like that, concepts of momentum and impulse makes our life a lot easier, right? So like imagine collision of cars, right? So if you try to study this in terms of forces, this is a very complicated process. You cannot study collision just using forces, but concept of momentum makes our life a lot easier, right? So that's why it's very useful. And it's very also important in physics, a very important concept. So these concepts, actually basic concepts, we use everywhere in physics. It's not just the classical mechanics. This is also setting up the stage for the whole physics. So later, let's say you're gonna follow a career in physics and you be a quantum physicist or nuclear physicist or particle physicist. These concepts are still there, right? So you still use energy, momentum, potential energy, whatnot, right? So these are not only valid in classical physics, these are the fundamental concepts in physics we use everywhere. So that is why they are important. So up to this point, we study motion in one dimension, two dimension, three dimensional. So it's called linear motion, right? So in linear motion, we first study the kinematics, and then we introduce the concept of force, and then energy, and then momentum. And at this point, now we go to another type of motion, circular motion or rotational motion, right? So we're going to study rotational motion. So again, we go back. So in rotational motion, we study kinematics, right? So just the rotation without considering the cause of the rotation, right? So we're going to, in a sense, study the analog of kinematics in rotational motion. And then we derive our equations that gives us, for example, angular position of an object, angular velocity of an object, and angular acceleration of an object. So as I mean, probably if you guys are a little familiar, these are just the same equations I just showed you in a couple of minutes ago. These equations, they are the same equations in rotational motion. So actually, we're not going to be deriving anything new, right? So these are just the same type of equations in rotational motion. So instead of talking about position of an object in space, we are talking about angular position. Instead of the velocity of an object, linear velocity of an object, here we are talking about angular velocity of an object. And then instead of linear acceleration of an object, here we're talking about angular acceleration of an object, but the equations are exactly the same. So we're not going to be deriving anything new here, right? So everything we have learned at the beginning was still applicable here, right, in rotational motion. So again, it's very important to get the things, learn, understand things we learn at the beginning. So that's what I want to emphasize here. When we start the course, right, the first couple of weeks are important because here we are going to derive these fundamental equations, and they are going to be the same for the rest of the course. So it's very important to understand the first couple of weeks. Okay, the rest is just going to be very easy, I believe. And then, so this was the analog of kinematics in linear motion, as I said. Now, after learning these, like angular motion, we're going to introduce the cause of the rotation, right? So remember, in linear motion, first we study kinematics, and then we introduce the concept of force. That is the cause of the motion. Here we do the same thing. We study circular motion or rotational motion, and then now we introduce the cause of the motion, which is also related to force. So this is what we call rotational dynamics, right? So first, In this course, we start with kinematics, and then we learn dynamics, introducing the concept of force. Now we go back to circular motion, so it's again kind of kinematics. And then we introduce the source of the rotation, which is called dynamics. So rotational dynamics. So kinematics, dynamics, and rotational kinematics, rotational dynamics. This is how it goes. And this is going to be the end of the course. So we're going to end with the rotational dynamics, and then we're going to study equilibrium. These concepts are very important in engineering. So the classical mechanics is the basics of mechanical engineering, civil engineering. So especially for civil engineering, is the rotational equilibrium is very important concept. So these are going to be, if you're going to be following any career in engineering too, these are going to be fundamental concepts you're going to be doing, learning. So this is the physics AP Physics 1 course that we're going to be doing hopefully pretty soon. So I think that's it. So let me know if you guys have any other questions about the course or topics. Otherwise, I think this is all I have. You can put your questions in the chat box if you have, or just unmute and ask. Other than that, how much? Yeah, it's been almost 45 minutes. All right. Otherwise, I'm hoping to see you guys in the class. I think it was February 27th. Let me go back and double check the time. Yeah. Oh, January 26th. Sorry. Yeah. All right. So if there's no questions, then I wish everyone pleasant night. So see you guys on 26th. Good night.